Hello, my name is Andrei Bычkov, and I present you my joint work with Lev Pogudin on a problem in combinatorial computer algebra, which arises from the field of dynamical systems. We'll start with a toy example. Consider a system consisting of a single polynomial differential equation, like this one. We would like to transform the system into one with quadratic right-hand sides by introducing new variables. To do so, we can introduce a new variable y equals x to the fourth, and substitute it in the original equation. To find a differential equation for y, we derive a definition of y. For this, we differentiate the x to the fourth, and use the chain rule. Finally, we have obtained an ODE with the right-hand side being 4y squared, which is also quadratic. So, we have found a desired transformation. To be more precise, we construct a system with a quadratic right-hand side such that every solution of the original system can be lifted to the solutions of the new system. Let us formulate the problem we are going to tackle formally. Consider a nonlinear ODE system with a polynomial right-hand side. We would like to add new variables to transform the system into one with the right-hand sides of degree at most 2. The corresponding set of new variables will be called a quadratization. The number of new variables is called the order of quadratization. Optimal quadratization is a quadratization of the smallest possible order. And finally, a quadratization with new variables being monomials is called a monomial quadratization. Our goal is to find an optimal monomial quadratization as fast as possible. We restrict ourselves to the monomial case because it's simpler, often practical enough, and in some applications only monomial quadratizations are needed. The problem of finding an optimal monomial quadratization is NP-hard and APX-hard, which we'll discuss in more detail during the presentation. But why such transformations to quadratic systems are important? One answer lies in the field of model order reduction theory, which approximates complex dynamic systems with simpler ones. It turns out that there are dedicated reduction algorithms for quadratic systems, which often work better than the general ones. Therefore, it has been proposed by Chenjigu first list system of interest to quadratic form and then perform reduction. Since the ultimate goal is reduction, it's essential that the lifted system is as small as possible. There is also another way to utilize quadratic systems. Imagine a set of general chemical reactions with species A, B, and C. In nature, reactions with 3 or more regions are quite rare. Therefore, such complex reactions can be decomposed into either monomolecular ones or bimolecular ones. An object of our interest is chemical reaction networks with continuous time, which are modeled by polynomial ODEs. Reactions with many components lead to equations with high-order polynomials. Hence, a transformation of the input system into a quadratic one will lead us to a model of the desired chemical reaction network. Finally, there exist dedicated methods for solving quadratic ODEs numerically in a more efficient manner, which also combines very nicely with quadratic reduced order models. Before discussing our quadratization algorithm, let's first review the earlier approaches to solve the quadratization problem. To the best of our knowledge, the quadratization algorithm was first proposed by Gu. The proposed algorithm is used mostly for theorem proving, and its optimality deeply relies on the random factor. The algorithm is formulated as follows. Introduce arbitrary new variables until a quadratization is not found. For example, the order of quadratization could exceed even 10 for this simple example. Recently, an approach to solve monomial quadratization problem was proposed by Matthew Emery, François Fache, and Sylvain Soliman. The algorithm is quite efficient and practical, but for some cases is not optimal. The core of the algorithm is encoding an input into the max-SAT problem and using a SAT solver. The NP-hardness of optimal monomial quadratization problem is proved the similar way. Let's discuss this approach in more detail. Imagine an n-dimensional space where integer points represent monomials. For example, for a 2-dimensional case, we'll label axes as x and y. Then, the value of each axis represents the associated variable to the power of this value. For example, a point with coordinates 2, 3 is a monomial x squared y cubed. So, the authors restrict a search space to set M, defined as follows. For each I, consider the number di to be maximum degree of variable xi in the ODE system. The set M is defined to contain the monomials with degrees of xi that do not exceed di. We'll illustrate it on a simple example. dy is 4, the horizontal line, and dx is 2, the vertical line. Thus, the set M of the example is a set of integer points inside this rectangle. It can be proved that the set M always contains some monomial quadratization. The algorithm proposed by Emery and Soliman searches for the smallest monomial quadratization inside the set M. For example, the monomial quadratization of minimal order that can be found inside is xy, x squared, y squared, and y cubed. However, our algorithm found a quadratization of a lower order, xy squared, y cubed, and x cubed, which does not lie inside the set M. Therefore, the restriction to the set M may produce a non-optimal quadratization. It would be interesting to find an analog of the set M, always containing an optimal monomial quadratization, as this would allow us using powerful set solvers. For all examples we have considered, the following set worked. From now on, we present our approach to solve the quadratization problem. First, we encode the problem in a graph language. So, let's take an input system of ODEs and make it a root vertex of a graph. Now, we build edges from the root into vertices that contain new variables. We can continue this process, for example, for vertices labeled with x cubed and y cubed, leading to a common child with two new variables. In general, each vertex contains a set of new variables z. And by repeating the described process, we can eventually find a vertex, containing a monomial quadratization of the input system. In the picture, we mark quadratizations as red vertices. Now, we can reformulate the problem of finding an optimal monomial quadratization as a problem of finding a red vertex with the shortest distance to the root. We must also mention that the graph itself is often huge, even for simple examples. Thus, we need an efficient way to traverse it. In this case, we use the branch and bound approach to explore this search space in a recursive manner. Here is how we put the problem in the branch and bound context. The search space will be a set of all monomial quadratizations of the input system. We associate for each vertex a subproblem, which is a set of monomial quadratizations containing the vertex. And the objective function we want to minimize is the number of new variables in a quadratization, which is the same as the shortest distance to the root we mentioned earlier. Before we start discussing the algorithm in more detail, let's introduce some properties of subproblems on the example. Consider a scalar ODE and associate a subproblem with 0 new variables. Now we introduce a variable z1 equals x cubed and obtain a new subproblem. Let V be the set of generalized variables, consisting of original variables of the input system and new variables. In our case, we have 1 and x for the first subproblem, and we add x cubed to them in the second subproblem. We also define an auxiliary variable v squared of all pairwise multiplication squares of variables in V. For the first case, we obtain 1, x and x squared, and for the second one, we gain additional x cubed, x to the fourth, and x to the sixth. And the final property is a set of non-squares, ns. It consists of all the monomials in the derivative of v that are not in v squared. In our example, it's all the monomials from the first subproblem and only x to the fifth from the second one. It's important to note that the subproblem is a quadratization if non-squares is an empty set. As we can see, the second subproblem is not a quadratization. Our algorithm is implemented as a recursive branch and bound step. An input of the algorithm step is the input system of ODEs, current subproblem, and an optimal monomial quadratization found so far. In the first step, we check if the subproblem is quadratization. If so, and has fewer variables than the current optimum, mark it as a new optimum and return. In the second step, we apply pruning rules and return if at least one of them is true. In the third step, we generate a set of child subproblems and heuristically sort them. And in the final step, we call the recursive step of the algorithm to each child subproblem. As you can see, there are two areas of optimization: pruning rules and heuristic branching strategy. So let's start the discussion with the branching strategy. For the given subproblem, we'll construct the child subproblems as follows. First, we choose any monomial among the non-squares with the smallest possible p, product of its degrees with the addition of 1. For our example, it will be x cubed instead of x to the fourth. And for every decomposition of the chosen monomial as a product of two monomials, we define a Charles subproblem by adding decomposition factors to generalized variable v. In our case, the new subproblem will be x squared and x cubed. We choose a score function p because it's twice the number of representation of a monomial, and therefore we can minimize the branching factor by minimizing the score function. We define a pruning rule specification as a Boolean function which is true if the problem cannot contain a quadratization of the order less than m. Pruning rules can significantly speed up the algorithm, and we present two rules that substantially did it. The first one is a rule based on deriving a quadratic upper bound, and the second one is based on square-free graphs. Let's start with the rule based on quadratic upper bound. Consider a subproblem with generalized variables v and a set of non-squares ns. Assume that it can be quadratized by adding a set W of new variables. This would imply that non-squares are inside the squared union of given variables v and the new variables W. This yields a bound of the size of non-squares. Since we know v and ns, we can find a lower bound for the size of W. This rule, although it's simple, significantly improves the performance of the algorithm. The rule based on square-free graphs is more complex, and therefore we need to discuss what square-free graphs are. Assume we have 5 monomials, such none of them is a square. Assume also that there is a set V of monomial new variables such that its size equals 4 and each monomial lies inside V squared. Since none of the monomials is a square, it can be written as a product of distinct variables from V. We can therefore think of it as a graph, with vertices being elements of V and edges given by monomials m. One can check that every graph with 4 vertices and 5 edges must contain a 4th cycle. Then, for some numbering of elements in V, we can write down edges m and obtain m1, m3 equals m2, m4. Thus, by checking all the pairwise products of m are distinct, we can verify that size of V number of vertices larger than 4. In order to take into account monomials that are squares, we consider not just graphs but pseudographs. A pseudograph G is called C for star free if there is no cycle of length 4 in G, with every 2 adjacent edges being distinct. Repetition of edges and vertices is allowed. The illustrated graph is C for star free graph. It has a cycle of length 4, it just contains the vertex with self-loop 2 times in a row. We define C of nm as the largest possible number of edges in a C for star free pseudograph, with n vertices and most m loops. Number C of n0 is the maximum number of edges in a C for free graph, and has been extensively studied. In this pruning rule, we use the exact values of C of nm, found by exhaustive search for n less equals 7. For n larger than 7, we use the upper bound for it. The pruning consists of first, finding a large set of non-yet quadratized monomials with all pairwise products being distinct, and second, interpret them as edges in C for star free pseudograph and use C of nm to get a lower bound on the number of vertices, that is, new variables to add. This rule also substantially improves the performance. Now we compare the proposed pruning rules. As you can see, the second and more complex rule has better performance than the first one for the most test cases. However, their combination has the best performance in general. Finally, let's compare our results with the Biochamp software that implements the algorithm of memory function Solomon. Here we either find a quadratization of lower order, or have a better performance. Sometimes even both happens. Let us summarize what we have discussed so far. In our work we have presented the first practical algorithm for finding an optimal monomial quadratization. Our implementation compares favorably with the existing software, and allows to compute quadratization for these systems which couldn't be tackled before. All our work can be found in QB repository on GitHub, where you can check out our Python package. We'd like to mention several interesting open problems. Consider a small example. Optimal monomial quadratization for the system has order 3, with new variables x cubed, x to the 5th, and x to the 6th. Although, if we collect monomials into a polynomial and replace x plus 1 with y, we will now have a system with optimal monomial quadratization of order 1, with a new variable y to the 6th, hence x plus 1 to the 6th. This and more general approaches show that polynomial quadratization may be of a smaller order than an optimal monomial one. Therefore, it's interesting to design an algorithm for finding an optimal polynomial quadratization. Another open problem we mentioned earlier is finding a finite set of monomials, which must contain an optimal monomial quadratization. This will allow us to use powerful solving techniques. The third open problem is how to search for optimal monomial quadratization if negative powers are allowed. We proved that if we introduce a variable of a particular form for each monomial in the input system, this set of new variables will be a quadratization. For example, consider an ODE system. We introduce variables y cubed divided by x and x cubed divided by y that satisfies the proposed form. As we can see, there are indeed a quadratization of the input system. And the final open problem is designing a faster algorithm for approximate quadratization, with guarantees of quality of the approximation. In our paper, we have shown the reduction of the APX hat to some set cover problem to the problem of finding an optimal monomial quadratization. Thus, we have high hope for finding an approximate algorithm. That's all by now. Thank you for listening. See you in the discussion session.